In this video, I'm going to talk about the commentary of the mathematical modeling point, which is, again, as I said, it is in ASCE 41. So in the commentary, they are giving us some basic assumptions regarding the mathematical modeling, and already I have mentioned it before. For two-dimensional models, so now they are starting with this word. For two-dimensional model, this means that it is, as I said, permitted if you are going to use the two-dimensional models based on the two conditions that we have mentioned before. Okay, based on the two conditions that I have mentioned before. Let's go back and revisit them. These are the two conditions that we have already mentioned before in the previous video. Okay, now let's read this. For two-dimensional models, the three-dimensional nature of components and elements should be recognized in calculating their stiffness and strength. Take care of this word, stiffness and strength properties. For example, shear walls and other bracing systems may have L or T shapes, and this is very right. If you have a plan, for example, and you decided that you are going to have, for example, this line, which is line A or axis A, for example, you are going to use it for 2D analysis. Then if you are having T shear wall, for example, here, okay, or L, for example, okay, in this case you need to take this T section or L section of the shear wall, and you need to draw for it the force deformation relationship and take into consideration its three effect. So you need to, whenever that you are going to model it, you need to put the modeling or to model these parts with the inclusion of its three effect. Okay, how we can use this, how we can put this three effect into our 2D, actually it is based on having the force deformation relation of this element, which is T or L shape or any other three-dimensional cross-section. Okay, after having this relation, then we are going to use the stiffness that is related to this element, and we are going to talk about the secant stiffness here, the secant stiffness, as I'm going to talk in a minute. Okay, so for example, if we have shear walls and other bracing systems may have L or T or other three-dimensional cross-sections where contributions of both the flanges and webs, as I said, we have like flanges and webs, should be accounted for in calculating stiffness, that's the issue, and strength properties. Okay, that's right, because stiffness, it is related to deflection. Strength means that the shear strength that is going to be provided by the lateral resisting system under 2D analysis. In this standard, again, we are talking about, as I said, the standard here means ASCE 41, talking about this evaluation of existing structures, not new structures. Component stiffness is, component here means that the T or L. Stiffness is generally taken as the effective stiffness based on the secant stiffness to yield level force. Okay, I'm going to talk about this in this slide. Yes. Consider this is the relation between moment and rotation of whatever that you have, T section, for example, wall. Okay, let's assume something like this. And the moment rotation relation is being given by this curve. Okay, this is what we call it, the moment versus rotation curve. Then we are going to have, at a certain point, we are going to have a secant stiffness, means that we're going to draw a line that is going to intersect with the moment rotation curve at a point. This point is going to be indicated as the M yield, okay, M yield of this element. If we're talking about something related to concrete, for example, maybe it's M cracking. If we're talking about something of the yielding of reinforcement, we're talking about some reinforcement or something like this, then we are having something like this, a line that is going to cut the moment rotation curve at a point. This point is going to be the yield level force or yield level moment. From where we can get this force relation, and what is the criteria for putting the secant here or here or here, something like this. So this is a question maybe in your mind. So that's the that's the answer for it. Specific direction on calculating effective stiffness is provided in each material chapter for each type of structure system. So material chapter here means that if we're having RC chapter, we have steel chapter, wood chapter, and so on. So the indication or the direction of how to draw this relation and how to put this secant stiffness, it is not from here, of course. This is only like giving you an example, okay? But it's not what you should really use whenever that you have something related to T or L or something like this. It is going to be given and provided for you in the each type of structure system material chapter, okay? Examples. Okay. Another issue which is important also for us, whenever that we are going to deal with 2D analysis, we need to take care of the connection, especially for steel frames, okay, steel moment resisting frames. There is something what we call it panel zone that we need to take care of it, okay? We need to take care of it. The connection of this, or the flexibility of this connection, is very important to shape the total performance of the steel moment resisting frame. It is really important. This is what we call it the panel zone, the zone which is between the column and beams, and it has a great effect on the seismic performance of the 2D frame analysis modeling if we are going to take care. So if we are going to use 2D analysis, then we need to take care of panel zone and think about how we are going to model it. Examples of where connection flexibility may be important to model include panel zones. This is for steel moment resisting frames, and joint region of perforated masonry or concrete walls. Okay, so the comment here regarding this issue is for nonlinear procedures, whenever that you are using nonlinear static, for example like pushover, or nonlinear dynamic like nonlinear time history analysis, okay, a connection shall be explicitly modeled if the connection is weaker than or has less ductility than the connected components. That's very important. You can use 2D analysis, okay, but remember well, if this connection is going to be weaker than or has less ductility than the connected components, in this case you need to model the connection, explicitly model it. Or if the flexibility of the connection results in an increase in the relative deformation between adjacent connections of more than 10%. This means that whenever that you are going to use 2D analysis, and of course also 3D analysis, but I'm placing an emphasis here on these points because 2D analysis, maybe you are thinking about simplifying everything, but actually there are some regions that you need to take care of because they are going to highly influence the seismic performance of the 2D analysis that you are conducting or performing. Among them is the panel zone, or in general the connection, and especially when the connection is weaker than or has less ductility than the connected components. That's really important. You can have a very, very rigid column and very rigid beam, but the connection in between, it is very flexible. Then the total performance is not going to be as you are expect if you are simplifying this joint. Okay, you need to explicitly model it in a proper way. Okay, so this is actually the main issues that I want to discuss regarding this. This is related again. I'm talking about the mathematical modeling using two-dimensional. Okay, two-dimensional. So we need to take care of this whenever that we are using two-dimensional. Remember well that if we have 3D components like L or T-shaped components, we need to take them into consideration. Okay, and the other issue is related to the joint. Okay, so we need to take care of the joint, especially panel zone for steel moment resisting frames, or the joint region of perforated masonry or concrete walls. And remember well that we need to take care of them because they are going to have a great influence on the seismic performance of the 2D analysis. Thank you for listening, and see you in the next video.